When you close a door, you probably don't think twice about the piece of metal keeping it shut, but the hinges, locks, and handles surrounding us have quietly evolved. They are now packed with sensors, microprocessors, and advanced metallurgy. Every time you turn a handle or swipe a badge, you are interacting with a computer that instantly authenticates your identity and calculates environmental variables. The buildings we live and work in act as automated networks designed to predict our needs and protect us from physical threats. The jagged metal key you carry in your pocket is rapidly becoming obsolete, replaced by digital systems that scan the unique geometry of your face to grant access. This bar chart tracks lock installations over the past year. While traditional mechanical locks remain flat, the line for biometric lock installations surges to 900,000 units deployed globally. Security also involves keeping out microscopic intruders. A standard steel door handle can harbor millions of pathogens, acting as a transfer point for infectious diseases every time it's touched. To combat this, engineers developed handles forged from antimicrobial copper alloys. When pathogens land on these surfaces, the copper ions pierce the cell walls, destroying 99.9% of the bacteria within 2 hours. This specific alloy formulation is already actively installed across 500 hospitals in France, Germany, and Spain. The metal on our doors now functions like a secondary immune system for the building, actively breaking down biological threats before they can spread to human hosts. This pie chart reveals a hidden vulnerability in construction. Exactly 18% of all architectural hardware sold worldwide is counterfeit, slipping into the global supply chain through unverified vendors. These knockoff hinges and latches lack structural integrity. During a fire or under extreme mechanical stress, they can warp or snap, compromising the safety corridors of high-rise commercial buildings. To bypass the counterfeit market entirely, legitimate engineers developed proprietary metal blends, specifically alu-zinc composites. An alu-zinc composite is a highly engineered alloy that combines aluminum and zinc to maximize both corrosion resistance and structural capacity. This dual-gauge graphic shows the precise advantage of this new alloy. Compared to traditional brass, the alu-zinc composite reduces weight by 30% while simultaneously boosting tensile strength by 20%. Building massive, secure commercial towers requires advancing the periodic table. Engineers have to innovate at the chemical level to keep modern architecture standing. Even the glass surrounding us is adapting. Motorized window actuators have turned fixed glass panels into mechanical lungs that open and close to let the building breathe. This schematic illustrates the artificial intelligence driving those windows. The central processing node ingests real-time data on wind speed, solar heat, and the internal HVAC system, automatically calculating the precise angle to open a window to minimize energy consumption. Inside the building, electricity is merging with the furniture. Heavy, static shelves are being replaced by modular slide rails with embedded LED lighting systems. The demand for these illuminated fittings is massive, with 750,000 units shipping in a single quarter. Hardware designers are also actively manipulating sound. They have engineered innovative soft-close latches equipped with advanced hydraulic dampers that absorb the kinetic energy of a moving door. Over 1 million of these specific latches have been installed in urban apartments, reducing the acoustic shock of a slamming door by 75%. Modern architecture manages its own temperature, illuminates its own storage spaces, and silences its own doors entirely on its own. In high-moisture environments like bathrooms, raw metal rapidly corrodes. To stop this decay, manufacturers apply hydrophobic coatings. A hydrophobic coating is an ultra-thin chemical layer that repels water, forcing droplets to bead up and act like microscopic vacuums, picking up mineral debris and washing it down the drain. Consumers have purchased nearly 5 million of these self-cleaning shower hinges to prevent long-term water damage. Physical wear isn't the only threat hardware manages. Commercial sliding glass doors weigh hundreds of pounds and carry enough kinetic force to crush human bone if they close unexpectedly. To prevent injuries, engineers developed anti-pinch mechanisms. These use embedded sensors to detect physical resistance and trigger a mechanical override in a fraction of a second, a safeguard currently active in 300,000 commercial doors. From repelling microscopic water damage to halting a heavy sheet of moving glass, The intelligent hardware is constantly calculating and rapidly neutralizing physical risks to keep itself and the people around it intact. The construction sector has historically been one of the most resource-intensive and polluting industries on the planet, heavily reliant on mining raw ore to produce steel and aluminum. This flowchart maps out a shift in material sourcing. Instead of extracting new ore, smelters are taking industrial waste and scrap metal and forging it into modern fittings. Today, 42% of all the hardware installed in green-certified buildings comes from recycled metals. The biometric scanners, the lightweight composites, the automated window actuators, and the kinetic sensors are no longer isolated components. They communicate through centralized building management platforms to form a unified, intelligent grid. The infrastructure around us has woken up. It is a highly tuned, constantly observant machine designed to conserve resources while keeping us perfectly secure.